Welcome. My name is Dan Stieler with PowerFilm Solar, and today we're going to talk about practical design considerations for energy harvesting with solar. The first thing to talk about is the components that a solar energy harvesting system consists of. And so there are four basic things. Typically you'll have a storage element of some sort, whether it be a battery or supercapacitor. And this allows you to bridge time periods when there's no light or low light levels and the solar isn't able to generate enough power. So for example, if you had a sensor system that was installed inside a building and running off the typical indoor light from the building, and you wanted it to run at night even when the office or building was shut down and the lights were off, you'd need some sort of energy or some sort of storage element to operate the system during that time period, and then rely on the solar to charge up that storage element and operate the system during the day when the lights are on. The second item is a charge controller or energy harvesting PMIC. Typically when you're talking about energy harvesting, they talk about having a PMIC rather than a charge controller. And the PMIC itself is what takes the small amounts of energy from the basically whatever your energy harvesting power source is, in our case solar, and is able to transfer that efficiently with a very high efficiency to the low power electronics and the storage element that you're powering. And so the PMICs have lots of different features, things like power point tracking and other optimizations that allow you to get the maximum power from your generating element. They also have features like being able to turn off and on the RF radios if you have an RF radio you're using, so it doesn't, or turn on and off the switcher so it doesn't interfere with your RF radio if you have an RF radio you are using. Allow you to set different types of battery charging profiles, things like over and under voltage, and so they're highly feature rich and customizable. The third item would be a solar panel in our case, and so this is going to be what is generating power for the system. If it's indoor, you might choose a panel that's optimized for indoor light. If it's outdoor, you might choose something more optimized for outdoor light. There are some differences, and we'll talk about them in a little bit. And then the final element is, whatever kind of low power electronics you're looking to operate with the energy harvesting system. Next, I want to talk a little bit about light itself, because light is kind of something that we frequently take for granted. The fact that sunlight and indoor lighting are really not even remotely close to the same type of light and will require very different types of solar panels to effectively collect power in one place or the other. And so if we look at outdoor light, efficiency is measured at STC, which are standard test conditions. For solar energy, that's AM 1.5 solar spectrum, and so that's the spectrum of the solar energy coming, or the spectrum of the solar light coming through 1.5 Earth atmospheres. 1,000 watts per meter squared, which is the amount of light that you would see through that level of atmosphere on a good clear day. And then 25 C, which is the temperature of the actual solar panel during the test. And so now 25C, all of these can be a little bit weird. They are just test conditions. So the solar spectrum varies depending on where you're at in the world. It varies depending on what time of year you are operating in, with more or less particulates in the air. If there were, say, wildfires nearby, or if you were near an agricultural area and they were harvesting a crop, all that dust and stuff will change the solar spectrum slightly. It will also tend to cut down on the total power coming out of that's available for the panels. So 1,000 watts per meter squared, you could be up to 10-15% more than that depending on where you're at. You could be certainly much less than that if there's clouds or other things that are obscuring the sun. And then the 25C, most panels don't actually run at 25C when you have them out and deployed. Even on cooler days, since they're absorbing light, they're absorbing infrared energy, a lot of the time the panels are going to be running in the 30 to 40 degree C range. And that actually changes the overall power output of the panels, because solar material tends to change, actually tends to decrease typically with its total power output as you heat it up. So efficiency, when you talk about panel efficiency, that's really the power per unit area. That's all it really means. Is if you have a higher efficient panel, it's going to take less area, deployed area, for you to get the same amount of power. And that's under standard test conditions. There's some things that some technologies absorb light a little bit better when they're off axis versus tracking directly with the sun, and so their efficiency over the course of or the total power generated or collected over the course of a day might be more comparable with a higher efficiency panel, even though that peak efficiency in ideal conditions is actually less. There's a good tool out there that's called the NREL PV watts calculator. If you just hop on Google, type in NREL PV watts, it'll bring it up. It allows you to estimate the amount of solar power available at any given place in the country and even the world based on the time of year and the location and all those sorts of things. And so it can give you kind of what would be an expected average for a solar panel deployed in that region. And typically what I'll use, if I'm looking for a worst case scenario, I'll look at something like the Seattle area in the U.S. if it's going to be deployed in the U.S. because that'll give you one of the more stringent use cases if you're building something that you want to be able to deploy anywhere outside and give you an idea of what you can expect for the worst case power availability. Light intensity outdoors is 100 to 500 times higher than indoors, and so that also makes a difference indoors, which we'll see in a little bit. So when we look at indoor lighting, off on the left hand side here there's a set of graphs that are showing what the spectral distribution is for various indoor light sources compared to outdoor lighting. And so you'll notice that first of all, this is the wavelengths available here are truncated. In the previous slide, if we go back to the previous slide, you can see the infrared light, the light available from the sun, extends way out to about 25 nanometer light. When we come back down to the indoor lighting, it cuts off 750, 800 nanometers. So it's a much more limited spectrum. In this plot, the solid line is actually what the AM 1.5 spectrum would look like in this area. Then there's incandescent lighting, and you can see that's the dotted line, and that actually extends way out into the infrared spectrum. You can see it's actually still building intensity as you get over to that about 750 nanometer range. And then there's the higher efficiency indoor lighting sources like the fluorescent LED, which have become more and more common in indoor light environments. For these higher efficiency light sources, you can see the spectrum's much more limited. It's much more focused on the visual spectrum. There's not a lot of infrared light there. And so that means that a cell that you might have, a solar type material that you might have outdoors that is very high efficiency, and a solar material that you have outdoors that's a lower efficiency, depending on what they absorb and where they absorb at, they could be very comparable, or even the lower efficiency material may even produce more energy than the high efficiency material indoors because the actual available power is much more limited in wavelength than in the outdoor case. One of the typical lighting scenarios for indoor lighting, are 50 to 1,000 lux, maybe up to 3,000 or 4,000 if you have really bright lighting, which is compared to 130,000 lux for outdoor lighting. So 130,000 lux compares roughly to the 1,000 watts per meter squared. And the advantage of indoor lighting for like a energy harvest application is frequently it's much more predictable. You know the lights are going to be on for 8 or 12 hours a day and off for the other parts, so you can kind of place your device in an area where you know what the lighting is and you know what the cycles are going to be, and you can predict how it's going to perform much easier than a outdoor light environment where you have nature to contend with, and it's hard to tell sometimes how much absolute light you can get. Again, you can estimate it and get averages with the NREL PV watts calculator, but you still have to contend with nature. This slide shows some typical indoor lighting scenarios. The panel off on the left-hand side you can see is 11 by 3.7 centimeters, and so these scenarios roughly tell you what you could power with a panel of that size, and what a location might be. So you can see 50 lux would be a fairly dark location. It might be under a desk. You'd still be able to power something like a Bluetooth sensor beacon that's updating about once per minute. If you move out from under the desk to a darker office space or warehouse space, you might be at around 200 lux, and that could power a full Bluetooth sensor module, updates about once per second. Moving into a brighter environment, say a retail sales environment, a grocery store, something like that, or near a window, you may be getting 1,000 lux or a little bit more. In that case, you can operate something like a Bluetooth sensor module with 10 updates per second. Then outside, in the shade, you might be around 25,000 lux, which would give you enough power to operate a Bluetooth low energy gateway partially. And of course, then you get out into the 100,000 lux range, direct sunlight, you can operate a gateway all the time. And so these scenarios with what you can operate, or estimates of what you can operate, are really based on that 11 by 3.7 centimeter cell size. So going into a little bit more depth with indoor versus outdoor efficiency, you can see on this slide there's some efficiencies from different solar technologies. Amorphous silicon outdoors about 6%, crystalline silicons around 18%, CIGS solar material might be 8.5% outdoors, triple junction gallium arsenide 30% outdoors. And so you can see on the right hand side then the plot shows the solar power generation versus light intensity for an indoor light environment with a 3000 K color temperature white LED. And interestingly enough, in this case, you can see the amorphous silicon cells actually end up producing more power than the other types of cells. And there's multiple reasons for that. So when you look at the light spectrum, like we talked about before, it's much more limited. You don't have all the infrared light. You only go out to about 750 nanometers. And so what does that do? Well, that knocks the triple junction gallium arsenide out of the running right away, because it has one junction in there that's really looking for that infrared light, and without that infrared light, it's basically starved for photons. And when I think about a triple junction gallium arsenide cell, it's basically 3 diodes in series, and if you have one of the diodes starved for photons, that means it's not producing as much current. So that's going to limit the amount of current out of the full solar cell. Then if I look at something like the CIGS cell or some of the smaller cut crystalline cells, they tend to have higher parasitic leakage due to CIGS. It's really native to the cell itself and the technology. For the crystalline cells, it depends on the cutting process and what types of leakage paths or shunt paths are formed. But in low light intensity areas, that can really dominate the performance. If you're losing losing electrons due to leakage in the cell itself, they're never making it out to the real world. At high light intensities, at 130,000 lux, not a big deal. You've got lots of power being generated. You're not going to notice little loss. When you drop down to a couple hundred lux, it can become a really big deal. The other thing to note about indoor, when you're comparing different solar technologies indoors, is that there's no light standard. That we talked about earlier the standard test conditions for outdoor light and outdoor testing for solar, and there's a well-defined set of conditions. When you're looking at indoor lighting, there is no set of standard conditions. So manufacturers will test whatever way they have equipment for, or whatever way they think is useful, and that doesn't always align. They don't always align with each other, right? So one manufacturer might test with fluorescent lighting, one might test with warm white LEDs, one might test with cool white LEDs, and so it's hard to get an apple-to-apples comparison. And so to really get that apple-to-apples comparison, procuring the cells and actually testing them side by side in whatever your lighting environment or whatever that relevant light environment is for you is probably going to give you the best information. Alright, so next if we talk a little bit more about the energy harvesting PMICS. For solar, it's really important that the PMIC has some sort of PowerPoint tracking integrated into it. That's because the solar cell operates on an IV curve, and you can see off on the right hand side of the slide here examples of a couple IV curves. And so an IV curve is the current output versus the voltage output. In a typical diode, you would see a curve that looks similar to this, only it would be flipped. You typically see it flipped upside down so that it would be starting at 0 and it would be racing up to higher currents as the voltage increased. In a solar cell, it's basically flipped upside down like this, but it's the same characteristic curve. And so you want to be able to have the energy harvesting PMIC choose a point on that IV curve that you can get the maximum power from the panel. And so there's basically 3 ways that they do that. There's a fixed power point where you use a resistive divider to set a specific voltage that you want the PMIC to collect power at. That's denoted by the gold-colored line on the graph here. There is a ratio power point tracking system where the PMIC actually will take and measure what the open circuit voltage is, and then it will go and collect power at whatever percentage of that it's set to collect at. And again, that percentage is actually set using a resistive divider when you're designing the chip. And so it may be that you want to collect at 75% of open circuit voltage. That's where you think the power point is on your cells, and so it will consistently measure open circuit voltage and then go and measure or go and collect the power or harvest the power at that 75% of whatever it had measured. And then the last type is actual maximum power point tracking. And so in this case, the PMIC will sweep the IV curve and do the calculation and figure out where the maximum power point actually is, and continue to reset and monitor that so that it's always collecting the maximum power from the panel. And so the plot on the right hand side gives you an example of one panel and what its operating IV curve would look like at 3 different light levels. And you can see how if you're in a lighting environment where it's changing some, having either a ratio power point tracking or a max power point tracking device is going to help you collect the most power, because the voltages as you go down in light intensity to very low levels start to decrease, and that shifts your maximum power point around a little bit. In full sun environments, if you're going outdoors where you have high intensity, a fixed power point tracker is probably just fine, because at high intensity levels the voltage doesn't change very much. You can go from 25% or 25,000 lux to 100,000 lux and the voltage really doesn't change a ton. But once you get down in the 200 to 1,000 lux range, there are some pretty significant variations in voltage. The PMICs, like we said before, are really there to maintain battery health or health of a supercapacitor, something like that, storage element. They're capable of very low power collection. That you only need 80 millivolts in a lot of cases and a microamp to start collecting power and putting it into a storage element or sending it to your device. Power consumptions are very low, less than half a microamp, and the converters in them, in most cases they're boost converters, right, going from 80 millivolt up to something that would be like a small lithium-ion battery or a supercapacitor at 2 to 4.2 volts, and they have a very, very efficient converter so that they're able to boost that voltage from the 80 millivolts or whatever your voltage is up to the storage element voltage. The nice thing about solar is a lot of the time you can get relatively high voltages, unlike a lot of the other energy harvesting generators. So the solar panel itself may be matched more closely to what your actual storage element is to begin with, which again further improves the boost efficiency. So if you are trying to charge a lithium-ion battery, it may be that your solar is already putting out around 2 volts at power point, and so it's only doing a boost, a 2x boost, which can be done with reasonably high efficiency, really high efficiency in this case. The next thing that you want to think about is how you're going to integrate solar into your products. And so there's, again, with the different solar technologies, there's different advantages and disadvantages. Looking at things like environmental requirements, physical requirements, and different types of connection systems. This slide shows some examples of solar integrated into different products. There's trucking refrigeration unit, there's asset tracking and monitoring devices, things like animal tracking, power for powering a powered window awning without actually having to pull or have an electrician come and hook up hard line power, a smart bike lock, many different types of applications. So when I think about environmental requirements, there's a few things that come to mind. One is the system going to be able to keep producing power when it gets dirty? You know, does it have some kind of self-cleaning capability? If you need something like a self-cleaning capability, you're going to want to look at something more like a ETFE front encapsulant versus a polyester front encapsulant. Now, the ETFE is more expensive, but there's a lot of data out there that shows that ETFE, being a fluoropolymer, has a very good ability to clean itself. And when I talk about cleaning itself, I mean when it rains or something, if you're outside and it rains or it's in an area that gets washed down, that water very efficiently takes the dust and dirt away off the surface, where something like polyester hangs onto the dust and dirt, and so it requires, you know, maybe some physical or mechanical something physically coming and touching it and brushing it away, brushing the dirt away, rather than just the water running off it to take the dirt away. Impact resistance, depending on what your solar technology is and what your application is, you may be concerned about having impacts from a rock or something in the area that might hit it, and, you know, moving to a technology that's in a more flexible or thin form factor without glass encapsulant may be desirable in that case. UV resistance, again, if you're indoors, UV resistance might not be a big problem, so you can go with a cheaper encapsulant like a polyester. If you're outdoors, you may need the UV resistance, or you will need the UV resistance, so you may want to go with something like, again, a ETFE or a fluoropolymer, something that does not break down and turn yellow or crack when exposed to UV long term. Shade tolerance, depending on the technology and how it's put together, shade tolerance can be a big deal. Something like a standard crystalline panel, if you shade one cell, shading that one cell can cause the whole power output of the panel to drop significantly, you know, down to very, very low levels. If you have something like an amorphous silicon or a CIGS product that has really, really long cells, so your cell might be 3-4 feet long, it may be harder to shade it with something like a bird dropping or a pole or something like that, or a tree. And so you may end up with a fair bit more power throughout the whole course of the day as shadows move around than you would if you had a crystalline panel or something with smaller individual cells that were series strung. Water resistance, of course, you know, if you're going to have it mounted outside, you need to have that resistance to water. If it doesn't have some sort of seal, it's not going to hold up long term. And then cost. And of course, cost is always a parameter. I wanted to stop here for a second and talk a little bit more about shade tolerance in environmental situations. So we get a lot of questions about, you know, can I put power on this or solar on this pole? Since we make a flexible solar panel, frequently, you know, it's the idea to be able to wrap it around something, and it's thin, it fits, it just blends right into that particular use case. And so with shading or partial shading in this case, there's a couple things to keep in mind. Anytime you can design with fewer cells, you're going to be in a better shape, because if you partially shade a single cell, you're going to get the full power output from whatever part's not shaded. If you partially shade a module that has multiple cells and you're able to shade a full cell in it, again, you're going to lose almost all of the panel performance. And so the picture on the right hand side here shows two different panels that are mounted in different orientations on a pole. And in this case, if you mount the panel like the one on the left hand side, this is bad design practice, you're going to see that each of these rectangles that are vertical on that pole are going to have different light intensities, and so your total output of that solar panel, the power available to collect, is going to be limited by whatever cell has the lowest illumination. And so when it's curving around a pole, it may be that cell 1 has the sun coming in directly on it, where cell 4 is mostly shaded. So you're going to be limited by that. If you move to something like the good design practice shown on the right hand side, in this case the cells are all running, they will all have equal illumination, whether they're illuminated from the left hand side, the middle, or the right hand side. Now the panel itself won't be fully illuminated at any time because there's always going to be some shading around there, but with each cell in equal illumination, instead of being limited to a low level of the lowest level of the shaded cell, you're just going to be limited by the amount of illumination on the full panel, which means that you'll get in that case you may be getting 80%, 75% out of the full panel versus 10% with the bad design. So how you mount stuff is very important when it comes to shading, and something that needs to be considered. Missed a slide there. Okay, physical requirements. For physical requirements, there's a few things to think about. Size and area. We talked about efficiency earlier, and so having a panel that is very efficient may be what you need for a specific application, because maybe you're limited on the amount of area that you actually have available. And the efficiency of the panel for outdoors technologies, there's a well-defined efficiency. Something like a crystalline silicon panel might be the right option if you're looking for something that's very high efficiency and you can use it outdoors. When you move indoor, again, there's no specific way that industry measures cells, but because of the limited light spectrum, you'll probably find that something like an amorphous silicon is going to provide more power for you when you're indoors than a crystalline silicon or one of the other types of products, a polycrystalline silicon, a CIGS, any of those types of things. This next physical requirement to consider is weight. So the weight would be a crystalline module. If you're looking at that, they tend to have a lot more structure. They're a lot more rigid. Some have glass, some have epoxies. That all tend to make it heavier. Something like a thin film panel is going to weigh less because it uses very, very thin plastic films, and may be, much, much lighter. It may be less than a tenth of the weight of the crystalline product. And then flexibility and conformability. If you want to wrap around something, if you want it to conform and blend into your device, it may be that a flexible product is what you need. When it comes to electrical integration, solar in general is not compatible with an SMT process. So there are different ways that you can, many different things that can be done to be able to integrate the solar. Here are some examples on this slide. The first one would be adding wire leads to a panel. So you could purchase a panel from the manufacturer with leads already installed, and then simply solder the wires to whatever your system is. Panels can be made with tabs on them that could be pushed through a through hole on a circuit board and then soldered by hand or with something like a wave soldering machine. Cells can have tabs and be surface mount soldered to surface mount pads by hand or with a soldering robot. Something can be done with, like down in the bottom left-hand corner, where you're using a connector. Flexible printed circuit connectors work very well with thin film devices, so you can have them actually mounted during your regular standard surface mount process and then come in and simply just push the panel into place like you would a flex circuit to a battery or something like that in a cell phone, for example. Backside contacts are available, front side contacts are available. Using conductive epoxy is a good way to connect solar systems as well, especially if they are using backside contacts. That can allow you, if you're using a backside contact with a conductive epoxy, allow you to actually put the system on a fully flexible printed circuit board. So, how do you get started? One of the easiest ways to get started exploring energy harvesting and how that fits your application is to go out and buy a dev kit. Here's a number of different dev kits that are available on the market currently for energy harvesting PMICS that are designed to work with solar. So, go out, do your research, figure out which PMIC is going to have the features that you need for your application, and get one of those and just start playing with it. Thanks for your time today, and we hope to hear from you soon.